So here's another free response question. This time is from the 2010 AP Calc exam. This is Form B of the exam, and it's a non-calculator question. And the setup here is that we have a graph given, and it's a graph of velocity. And the situation that's described is that a squirrel starts out at building A and then travels along a wire toward building B. The squirrel's velocity is given by the graph that we have access to, and we're asked a series of questions about the situation. So the motion here is just one dimension, back and forth along the wire between the two buildings. In part A, it says, at what times in the interval from 0 to 18 does the squirrel change directions, and then give a reason for your answer. Well, if you think about the way velocity works, velocity is the rate of change, or the derivative of position. So when velocity is positive, position is increasing. When velocity is negative, position is decreasing. So when velocity is positive, greater than 0, what that implies is that our object, or in this case our squirrel, is moving forward or up depending on the direction of the motion. And when velocity is negative, our object is moving backward, so back toward where it started. Now, the most commonly made mistake that I see get made in situations like this is we say, well, the squirrel's moving forward, forward, forward. The squirrel is stopped right here. That's not the case. The squirrel's moving forward, forward, forward. The squirrel's still moving forward. It's moving at a constant velocity of 20 feet per minute, probably not 20 feet per second. We don't really have any units to go with here, but 20 units of distance divided by whatever the units of time are measured in. So the squirrel's velocity is 20 on this piece of the graph. It's not stopped. The squirrel does not change directions right here. The squirrel is slowing down. Its velocity is getting closer to 0. And then at this point, the velocity is equal to 0. But as we cross this axis, that's where the sign of velocity changes from positive to negative. So the squirrel's going toward building B until t equals 9. And then when velocity becomes negative, that's when it's turned around heading back toward building A. And then it actually turns around again at t equals 15 and heads back toward building B, back with the positive velocity for the last 3 seconds, 3 minutes of the graph here. So at what times does the squirrel change direction? Changes direction at t equals 9, and it changes direction again at t equals 15. I think I pretty much already explained why, but you know, as always, if this was a test or a quiz, AP exam, give a reason. You'd have to write out the rationale that I just stated. In part B here, it wants us to figure out when the squirrel is farthest from building A. Now this word right here hopefully gets us thinking optimization, maximum. So what we're going to be looking for here is we're going to be looking for the maximum position relative to its starting point. So we want the maximum position. Squirrel starts at the top of building A, travels along the wire. So if this is building A, that's a horrible building. And this is building B, and that's not much better. Squirrel's moving on this wire toward building B. So the squirrel's moving toward building B, toward building B, toward building B. We said in part A that at t equals 9, the squirrel changes direction, moves back toward building A for a certain time, and then moves back toward building B. So when is the squirrel farthest from building A? That's going to be the maximum position relative to its starting point at the top of the building. So if we're looking for an absolute maximum and we have a closed interval, our candidates would be the endpoints of the interval, so t equals 0, t equals 18, and then also any places where our derivative is equal to 0. So if we're looking for a maximum position, maximum distance from the starting point, what we're going to have to do is we're going to have to recognize that we need the derivative of position. We're trying to maximize position. What's the derivative of position? Well, that's what we have a graph of. We have a graph of velocity sitting in front of us, and velocity is the derivative of position. So the other candidates for the absolute maximum distance, the maximum position, would be any time when the velocity is 0. The derivative of position is velocity, and velocity is 0 at those two times. So that would be at t equals 9, and then also at t equals 15. Now it says to find the time when the squirrel is farthest from building A, and it also says to find the distance that it is from the building at that point. So what we can hopefully realize right away is that this is not going to be the maximum position. The squirrel is at the top of building A at t equals 0. So that's not going to be the maximum distance from building A, since the squirrel starts moving toward building B for the first 9 seconds, 9 minutes of this time frame. At t equals 15, we hopefully realize that this is also not going to be the maximum. So I'm crossing it out. The reason why I'm crossing it out is because this would be a local minimum on the position graph. And if it's a local minimum, there's no way that it can be a maximum. The reason why it's a local minimum is because what happens is the squirrel, for the first 9 seconds, is moving toward building B, and then it changes and turns around at t equals 9 back toward building A. When it turns around and moves back toward building B for the last little piece of the time frame, the last 3 seconds, that happens at t equals 15. So 15, the squirrel is going to be closer to building A than it was at t equals 9. That's a local min. There's no way it can be the absolute max. So what we need to decide is whether or not the maximum distance from the top of building A happens at t equals 9 or happens at t equals 18. So to find the squirrel's position at t equals 9, what we're going to have to do is we're going to have to remember that the area between this velocity graph and the t-axis, so the area of this trapezoid right here, it's going to represent the total distance the squirrel has covered across that 9-second stretch. So the area of a trapezoid, I'm going to erase my little sketch of the buildings at this point. The area of a trapezoid is found by taking the average of the parallel sides. We call those the bases. So we take base 1 plus base 2, and the average of them would be those added together and then divided by 2. And then we multiply by h, and h would be the distance between the parallel sides. So for this trapezoid right here, we have the parallel side along the bottom measuring 9 units. Across the top, this would go from the x value or the t value of 2 to the t value of 7. So across the top we have 5. And then the height of that trapezoid would be from 0 up to 20. So the height would be here, and that would be 20. So the area of that trapezoid, or the position at t equals 9, is going to be found by taking the area of that trapezoid. So we're going to take 9 plus 5 divided by 2 times the height, the distance between the parallel sides, which is 20. And so what's that going to end up being? 14 divided by 2, which gives us 7. 7 times 20 should give us 140. So the squirrel is, we don't really have any units here, 140 feet, 140 meters, whatever the units of distance are, 140 units from the top of building A at t equals 9. Now if we wish to find what the squirrel's position is at t equals 18, we're going to have to be a little bit more careful. We know that its position at t equals 9 is 140 feet from the top of building A, and then the squirrel goes backwards for the next 6 seconds, 6 minutes, whatever the units of time are. So from t equals 9 to t equals 15, the squirrel is moving back toward building A. We're going to have to subtract that off of this 140, and the distance that the squirrel has gone backwards is whatever the area of this trapezoid is. So if you try to specify the dimensions of that trapezoid, we're looking at 6 across the top of that trapezoid, and across the bottom we go from a t value of 10 to a t value of 14, so that would be 4. And then the height of this trapezoid would be down 10, so 10 units. So the area of that trapezoid is going to be found by taking 6 plus 4 divided by 2 times the distance between the parallel sides. So what's that going to end up being? 10 divided by 2, which is 5. 5 times 10. So the squirrel moves 140 feet toward building A across the first 9 seconds, and then it's moving 50 feet back toward building A across the next 6 seconds, minutes, whatever the units of t are, and then the squirrel's moving back toward building B for this last little stretch. And so if we find the area of this trapezoid, and the dimensions of this would be, let's see, across the top we have 2 units, and across the bottom we have 3, and then the height would be 10. So the area of that trapezoid would be 2 plus 3 over 2 times 10. And so that would be 5 halves times 10. If if you multiply 10 by 5 halves, I think what you're going to end up with is 25. And so the squirrel moves 25 feet back toward building B across the last 3 seconds. And so the position at t equals 18 is going to be, let's see, 140 minus 50 takes us to 90. And then 90 plus 25 is going to leave us at 115. So what's the maximum distance the squirrel ever is from building A? Well, 140 units, and it happens at t equals 9.